The topic of this presentation, I think, falls very well with what's happening at this convention in Dallas. And on Wednesday, there will be a workshop on the use of these materials, what we call FRP, because on September the 2nd, the Institute published a code on the use of these materials. So my presentation will have two objectives. One, to tell you a little bit about what we intend by FRP, what is in the code, and invite you, if you need to know more, to go to the event on Wednesday. And then the other thing is to show you a number of applications that I think are representative of what is the potential of this material in the construction industry. The disclaimer is that obviously if I present you applications, they must have been done before the code was approved, right? So but I think the importance of them is again to demonstrate that the basis of the code is already validated in the work that we've done in the field. So as you can see from the slide, and again, I apologize, I'm not very much used to be at the podium, but it has to be recorded, so I will have to be stuck here. I tend to like to go around and be more engaged with the audience. But as you can see, again, two parts. In the first one, I will be refer a number of times to this document, 440.11-22. And by the way, 2 weeks after it was published, ACI presented it to the ICC membership, and it was voted 102 to 1 in favor of referencing this document in IBC. And if this were to be confirmed by the vote of the building officials via email, it will be part of IBC in 2023. That means this document will be referenced by the model code, and the implications are not only for North America, but they are for the rest of the world wherever IBC is adopted. The second part of this presentation, perhaps the one that I would think in a sense is more fun, is a number of applications where I've been personally involved. Before I get into the code itself, I just have a few slides. I just need to tell you a little more about FRP, so we kind of are on the same page. Why do we need these materials? Okay, the reason is very obvious, and for somebody like myself that for the last 15 plus years has lived in Florida, I can tell you that these pictures come from structures that are out there. So we need to protect reinforced concrete structures that have steel reinforcement as their reinforcing materials. And the methodologies that we use today that are part of the state of the practice are listed here. We increase the cover, we put membrane, we put corrosion inhibitors in the mixture, we cover the rebars with epoxy or we galvanize. But in a sense, we are just delaying the issue, right? Because eventually corrosion will get to our structure. So I think the entire idea to consider composites as an alternative to steel is to address the issue of corrosion once for all. Now, composites are just one tool in the toolbox as far as I'm concerned. I always say that steel is a blessing of God. It corrodes, but if you are in the interior of a building, like inside this room, what would be the problem in having slabs or columns or beams made out of steel RC? It's only when you are in an aggressive environment that this could become an issue. I will also mention something about sustainability during the presentation because I think there is other incredible opportunities for these materials that go beyond the addressing the issue of corrosion. So what do we intend today with FRP? And I will use the acronym throughout, I apologize, fiber reinforced polymers. The fibers could be many, but in reality, particularly if we look at the code, the 440.1122, we refer to glass fibers. What type? ECR. So this is E-type E, but CR for corrosion resistant. So we're using, if you wish, the latest generation of glass that is available in the marketplace. There is other types of fibers. I'm not going to get into that because otherwise this will last a few hours. They document, the code, we're at ACI today, references as a material specification an ASTM standard. This is very important. You as a designer or you as a contractor have the ability to reference a specification that tells you what is the quality of the material. And this document is ASTM D7957. By the way, the first edition of this document came out in 2017. We have just reapproved it, so there is the 22 edition, and the committee, the subcommittee in ASTM D30 is already working on another spec that looks at what we call the second generation of GFRP bars. So the GFRP bars have been with us for quite some time. So actually, if I say 30 plus years, I'm kind of not even saying the truth. Even in the late 60s, the U.S. Army Corps of Engineers was already looking at these materials. So there is a long tradition, even though the construction industry, in a sense, the Cinderella of many industries, has really not adopted composites as a main staple. If you look at other industry, for example, the aerospace, I think if you did fly to Dallas to come to convention, the plane that you were on had some composite reinforcement. Probably one of the cars that you're driving and so on and so forth. If you play golf, whatever. If you go fishing, the composites are everywhere, and they are coming now in the construction industry. In terms of the rebars that we have, they are of all the different shapes that we need in, to reinforce concrete. So they could be straight, they could be bent. And the characteristic is that made life a little bit difficult for us in terms of specifying. We don't have a standard deformation. So the deformation depends on the manufacturer. As you can see here, they could be helically wrapped, ribbed, sand coated, whatever, but just to ensure that there is a good stress transfer between the reinforcement and the concrete itself. In order to validate the quality of a product, we have to run a number of tests as specified by D7957. And these tests may not be the ones that are typically in the mind of civil engineers or engineers who deal with the reinforced concrete. I'll give you just an example. If you look at ASTM E2160, the enthalpy of polymerization. What is this? Something that we eat? No, this is to measure the degree of cure of the polymer that you use to make your FRP bar. So if this is a thermoset resin, for example, vinyl ester, you have to make sure that the vinyl ester is cured. Otherwise, the claim that you make on durability might not be there. So there is other tests that are relevant. I'm just going to show them to you here without the need for commenting. The other one is the glass transition temperature. So that magic number above which the quality of the resin may degrade. For the last, let's say, 2 decades, one of the things that we were asked, people like myself who have conducted research in this field, okay, you claim that there is no corrosion, but is there durability issues? Particularly if you think in terms of glass fibers that are used in GFRC, not FRP. The randomly distributed glass fibers that we add to concrete. We know the practice is that you use them only, in panels, for example, during the installation, but then they would eventually degrade in the alkalinity. So there was always this concern. Not only we have demonstrated that this is not the issue in the lab, but a couple of years ago, ACI itself funded a project where we went back to bridges, 11 of them, that had been already in place between 15 and 20 years. We drew coupons out of these bridges, we test them in the lab, and we determined that the level of degradation was minimal. So we could justify what we call the knockdown factors that we have now introduced in the code. In fact, these numbers are now closer to 1, the unity, as compared to the first or the latest edition of the guide that was issued in 2015. So I think in terms of the durability of the reinforcement itself, we have no doubt about that. And in fact, we design structures that will last at least 100 years. Now the code, very few words about it, and this is the cover. I hope that you will, go after it. As I think in terms of format, and I'll speak to that issue, is the twin brother of 31819. In fact, the code addresses, and you can see the statement there, provides minimum requirements for the materials, design, and detailing of structurally concrete buildings, and so on. So these are sentences, in a sense, taken from 318. Okay? In fact, we call this a dependent code. So the structure, you will see in a second, follows directly that of 318 itself. Some of the chapters or some of the topics are not covered in this first version of the code, and one of them is seismic design. A GFRP-RC can only be used today in a seismic design category A. Okay? In categories B and C, we would allow the use of this material provided that the lateral system is not GFRP-RC. Okay? So there is limitations, there is research going on. Actually, I mentioned this morning, I'm reviewing, an external reviewer for a beautiful dissertation that is part of a PhD program in New Zealand, where one of the key topic is really the seismic performance of GFRP-RC structures. There is other chapters in the 440.1122 that are not covered by the code, and you see the list here. So the numbering is the same. If you are familiar with 31819, this is nothing else but the twin brother. Chapter 12, we don't speak about diaphragms. Yes, we skip the plain concrete because plain concrete is plain concrete, go directly to 318. We skip chapter 17, the anchoring to concrete, and then 18, which is the earthquake-resistant structures. The other thing that I want to mention, even though there might be a question at the end, these materials are linear elastic to failure. There is no yield plateau. Can we design with them? There is no doubt, but you have to be aware of them. What are the implications from a structural engineering standpoint? And that's why we have refrained from going into seismic design at this point, is the fact that now we talk about deformability, not ductility. Okay? So the fee factors have been calibrated in the code on this concept of deformability, making sure that whereas in a steel RC structure, you look at the strain in the steel that has to be at least 5,000 microstrain, that strain in the steel would correspond to a certain deformation, and we make sure that with the GFRP, you attain the same deformation at ultimate. So the outcome is the same, but the driving concept is rather different. The other thing that this code does that is kind of maybe a surprise to traditional engineering concept is we allow both the tensile control failure as well as the compressive control failure. So not only we would allow the breakage of the rupture of the FRP at ultimate, but also the crushing of the concrete at ultimate. Actually, we tend to prefer the latter rather than the former because there is also some ductility in this type of thing. Then other things that make these materials different, and so there is a little bit of learning curve when you want to design with them, is the shear strength, the double action, the bond performance is different from that of steel. So even though the design procedures don't change much, you have to address this issue. And the implications are that sometimes the serviceability limit state, such as deflection or crack with control rather than ultimate state. So it's a very interesting dynamic here, and it all depends on the amount of reinforcement that you have. I don't think I want to tell you much more about this. Maybe I only have one other slide about fire, but please, I would recommend, if you're interested in this topic, to attend the workshop on Wednesday. The last thing I want to mention is, and this was a conscious decision that we made after a meeting at ICC in March last year, is that we removed fire resistance rating from this code. And so we're saying, look, if you have to design a structure and fire resistant rating is part of the design, then you have to convince the building official utilizing methodologies that go beyond what is written in the code. So this is a very conservative step that we are taking. I could speak volumes about this issue and the experience that we have had in lab tests, but because we don't have available ASTM E119 test results that we can present to the building official, I think it's better at this point to be on the conservative side. So with this, I'm kind of going to pause a second, not really to ask you for questions, but to have the ability to switch content, if you wish. Until now, I've been trying to be as scientific as possible, tell you about a great code, and now I'll tell you more about our experience and fly through pictures. Hopefully this will keep you wide awake. These are not iconic projects, okay? We're not really designing superstructures, but I think within the project themselves, you can see the potential of this material system. So I have 7 of them. I'll fly through them, and actually I see some of my colleagues from Aramco. One of the projects is their really, let's say, flagship, if you wish. And then maybe if there is questions about that, they can also help me in responding to this question. Let me start with the IDOC in Miami, Florida. Why do I bring this? This is a very simple structure that was taken down by Irma. We built this with composites. We designed it really as a pedestrian bridge. This should resist the Cat 5 hurricane. But the peculiarity of this structure, in addition to the fact that it uses not only GFRP, but basalt FRP rebars, is in the fact that we wanted to demonstrate 2 things. First of all, that not only you can build a structure made out of precast elements, but also that you can use seawater, let me repeat it, seawater, and this is for Pepe, instead of fresh water. So we are casting this in a precast yard in Miami. We're bringing in the water from Key Biscayne, and we're using salt water. Why? Because the presence of chlorides does not affect the concrete, and the presence of chlorides does not affect the reinforcement. So the message here is that if we were to think in terms of sustainability, now all of a sudden brackish water could be usable. All of a sudden, after an event that creates havoc in an island such as Puerto Rico, and you have no access to fresh water, there is nothing to prevent you from using seawater. So obviously, if you are in Dallas, Texas, you don't have to use seawater. This would be crazy. But the ability to use seawater, sea sand without washing it, opens up a host of applications. If you are a cement manufacturer, you don't have to control the chloride content of your cement anymore. You can use waste products as an engineering fuel without having to worry about the chloride content because of this issue. So again, this was kind of a little project. You can see the precast elements. And again, the other novelty here, you can see on the right-hand side, the piles. These are reinforced concrete piles. These are not PC piles. So an exciting project for us that demonstrated that you can go beyond the traditional construction, in a sense following the ABC approach that FHWA is encouraging for bridge structure. And again, here you can see it's nothing dramatic, obviously, it's not an iconic pier, but is a demonstration that certain things can be done. The next project is This was in Miami. This one is in Broward County, so you move a little bit 40 miles north of the city. And this is a bridge that is for a local community, but does not have a single pound of steel in it. And very exciting for us. This is the second bridge in the state of Florida that was built with this technology. There is more than just RC here. Actually, the RC is the cap, the pile caps, or the bends, and the GFRP deck. But there is other elements that are made out of pre-stressed concrete using primarily carbon steel, carbon FRP strands. We did something strange here just to show you how you can push the technology. And at the precast yard in Jacksonville, Gate Precast Company, we even cast actually 5 piles, but we use in this project only 3 of them, using GFRP bars. All of a sudden, you can go into what we call mild pre-stressing. So you can combine the pre-stressing of GFRP with conventional cage, and then you can come up with a solution that is acceptable. So this was a very nice experience for us. There is really no code that speaks to this issue, but we wanted to try it out, and the drivability of these piles was excellent. Again, I could go into details. I don't think it's necessary, but just to give you an idea that why GFRP in pre-stressing rather than CFRP is obviously because of the cost of carbon compared to the cost of glass. You know, there is a factor of, if you're lucky, 10 to 20 fold the cost of carbon compared to glass. So if you can go into mild pre-stressing, the advantages are obvious. Some of the pictures indicate that the GFRP cages being assembled. I'm going to stress this point for the ones of you who are in the contracting side of the house. One thing is to prevent corrosion, and this we all understand it. But the great opportunity that GFRP or FRP in general offers is the constructability. These materials are 1/4 the weight of steel. You understand very well what this could mean in terms of installation savings. We have recorded, for example, productivity improvement exceeding 54% at the end of the week when the workers are not as tired when they use FRP. So very interesting implications. Again, just pictures to give you a sense of what the construction was, nothing different from what you would do with the steel FRP. This is the deck, and again, a sea of FRP, very nice for us to recognize. And again, I'll have a picture later of a worker carrying a bundle of bars, and you would say, wow, that person must be rather strong. We conducted some load tests. This is the first one, May 1st, 2021. We repeated the load test almost a year after. And the entire point here is to say that there is, today we learned from Santiago Pujol not to use the word degradation of stiffness, but decay of stiffness. There is no decay of stiffness after 1 year. We do not expect it. But this is a very important point that we need to validate over time, because the modular elasticity of GFRP is 1/4 that of steel. Obviously, if you are cracking, the width of those cracks will be higher. If the cracks are wider, then your stiffness may decay. And what are the implications on the structure? This is something we would like to monitor. This is my favorite today because of the last slide. Okay, as of this actually happened to be published in Concrete International. So if you go back to your CI, we made the front cover for this. Is a very interesting project in Flagler Beach. So now, just imagine this: you are in Miami, you go to Broward County. Now we go further north, close to Jacksonville or Kennedy Space Center. And this is what is the result of the previous hurricane. So what happened to the A1A, which is the predecessor of I-95, the road that takes you from Miami to New York? Well, you cannot really use it that much if you look at the last picture on the right-hand side. It's not just the cost of reconstruction, is the implication that a loss of this type has on the economy of a community. It's just dramatic, okay? So the Florida DOT came up with the idea of doing not really a demo project, but phase one, building a seawall using a Secant-Pile system for the first 1 mile. And to us, this was a very exciting project for which, as a university, we contributed. And when I use we, it's really a royal we. All the work was done by consultant contractors under the supervision of the Florida DOT. As of today, it's still the largest project. No, actually, it might be the second largest. The one in South Carolina is probably bigger in Charleston. I'll show you that. But we're very close to being the largest, over 1 million linear feet of GFRP bars. These are the cages of the piles, okay? Very interesting, I think. The speed at which they were fabricated caused the contractor to hire 2 suppliers of the grout that goes into the piles because they could not keep up with them. So again, the cages are just traditional, but they were fabricated at a speed that the contractor could not even foresee. This is the method of application or the construction of the Secant-Pile. I don't want to go into details because there is nothing new here, but the contractor was extremely effective. Actually, the job was completed in 4.5 months, way ahead of schedule, for which there were benefits. One of the things that I want to mention here that maybe could be a concern for a contractor is a great thing if the FRP is lighter than steel, right? Because of the way you utilize it. But if you are doing an overcast pile and you have to drop the cage into the hole that is full of concrete, would the cage sink? We had no problems. And so again, this was a great experience. The other thing that we learned from this project, probably the nose is not necessary. Actually, the designer utilized the nose here for a previous job that we did where we did auger cast piles, but we think that now is no longer necessary and the cages could be just simply straight. Not only the Secant wall, Secant-Pile wall was made with GFRP, but also the cap, right? And here you can see on the left-hand side the cages, and on the right-hand side, the last picture is immediately after the end of construction. That's how the place looked like. This is the best picture. Nobody knows that there is a seawall, right? You agree with me? Wow, look at this. This is the best picture that I have today, and I'm really going to spend a few seconds on it. Look at the left-hand side. The left-hand side, this is the summer of 2019, just about the completion of the job. Again, you don't see the wall, right? You see the cap there, and you see the sand. Well, until almost a month ago, when Ian decided to cross the state of Florida. Now look at the beach. Where is that? The beach is back in the ocean, but the Secant wall is still there. And now, you could argue, if it were to be made of steel instead of FRP, would it still be there? Yes. But now, this is all contaminated concrete. Now, the seawater is impregnating the concrete. And so 10 years from now, if this were to be steel, I doubt you would have it. So the Secant-Pile served the purpose very elegantly. It was inspected by the EOR just immediately after the event, and we understand from the Florida DOT that there was no damage. But I think the entire point here is an issue related to durability. That wall will last 100 years, assuming that we don't get a bigger hurricane to take it out. But in terms of the durability, we have no doubt. Now, here is dedicated to my colleagues from Saudi Arabia. This is, without any doubt, the largest project in the world as of today. I hope that we will beat it soon. Again, it was published in Concrete International recently. Is a flood mitigation canal in a very exciting new city called Jazan. You see the geographical location at the southern tip of the kingdom, and this canal is a canal to protect the area of the city from floods that, believe it or not, I learned a lot out of this project. They also happen in an area where you think of this as a desert. So originally, the flood mitigation canal was designed using epoxy-coated steel, but then the owner decided that it was more logical to design or have a structure designed with GFRP, replacing the epoxy-coated steel with a material that would assure them a longer life. These are some of the pictures. I don't want to get into the details, but the only reason I show them to you is to indicate the magnitude of this project. Okay, very significant. And again, just to give you a dimension of it, look at the delivery of the material and the number of workers on the project. So this is for real. You don't do these things just for fun. You do these things because you believe that they meet the needs of the client first and society second. This is the placement of the concrete in one of the panels, but I was not there during construction, but I believe that most of the work, as indicated in this picture, was done at night because obviously of the control of the temperature. The last thing I want to show you related to this project is this table. Don't get into the details. Look at only the last column, where you compare the GFRP costs based on, as a basis, against the epoxy-coated steel. This is not numbers that come from us at the university. These come from the contractor. If you look at the last row, there is a 79% reduction. Okay, that means 21% savings. And you can see the only two items where you're spending more money is in bar supports. Why? Because the module elasticity of the bar is lower. So you need more chairs. And then you need more gloves because of the handling of the material. It might be more sensitive to the skin. But look at the cranes. Cost of the cranes, zero, because now you can move the bars in a different way. So these materials not only can be effective if you look at an LCC, a life cycle cost analysis, but they could be, favorable even on a first cost basis. So this is a very interesting data point. This is a project done, also this made the front cover of Concrete International. I'll bring it to you as quotation mark violation of the code, because in this case we are using basalt FRP, not the GFRP. So we had to get a special permission here, but it's a long story. But I just want to tell you that things are done not only in Florida, but also in our capital. So this is a very interesting building, and the contractor in this case was the one that really wanted to use the FRP. And I remember a conversation with him, and I said, what is the driver? And he said, in real estate is location, location, location. In my business is weight, weight, weight. So the driver for the contractor in this case was the ability to place these materials and really save equipment time, particularly crane time. So this is a floating slab, nothing major, 5,000 square foot of job, very, very tiny. But I think representative of the potential, the other potential of this material that goes beyond the durability issue, but you take advantage of other things. For example, if this had been extended to the balconies, you could have used the same concrete mixture without the chloride inhibitors. You could have saved $50 a cubic yard right there, but more importantly, use the same concrete. So you would only need one type of ready-mix truck at the site. The finishers would have finished the surface with the same type of equipment and the same type of skill. So I think very interesting. This is the picture that I kind of was referencing before. Look at the figure on the right-hand side corner. and you see a very tough guy, right, picking up a very large bundle of rebars. Try to do this in steel if you can, but with FRP you can. So very interesting. And this is the placement of the concrete. Another thing that we learned that is very nice, and one of our PhD students here is in the room and is following, say, Rogani, this type of application. If you step on a number 3 steel bar, unless you are my weight, you typically bend it, right? And once it's bent, because it's yielded, it will lose the cover. FRP is elastic, so you can walk on it, and then it bounces back. So you have a control of the cover that you would not have traditionally. The next one is my new residence in the Bahamas. I'm just kidding. It's not my home. I wish it were my home. But this is a project for an influential individual who lives in Coral Gables, Florida, who's building his home in the Bahamas. Second home, obviously. It's very close to the beach. Wants a Cat 5 home. And very conscious about sustainability. And it says, I want to use seawater. Not that I have to, but I just want to make a statement. So this is the construction of the home, and then you can see is for the foundation, the columns, the slabs, and also, I don't have slides here, for the masonry. Let me make a statement. TMS 402, which is the building code for masonry structures, it was just approved this summer with an Appendix D, D as in David, that allows the use of GFRP. So as the TMS 402 will be referenced by IBC, this is another location where the use of GFRP is allowed. And again, look at the vicinity of the sea, and I asked to go and inspect this job very often because it's not a bad place to be. So imagine sailing there close to the beach and saying, okay, anyhow. The last project is still underway. It's very exciting. This is the South Carolina low battery seawall. Actually, if everything goes right, you will see an article on this project in the November issue of Concrete International. This is in my mind, a historical rehabilitation of a wall that has been around for quite some time, 1670, in a very prominent location. And the refurbishing, reconstruction of this wall, as you can see from this list of bullet items, was intended to accomplish many things. And the contractor, and here you can see a cross-section of how the new wall looks like. There is, little piles and, to create stability, but I think the most important part for us are the slabs and the wall itself. And the phase 1 and phase 2 have been already completed. The contractors on top of phase 3. And you can see from these pictures what has been done. I mean, this is obviously with the drone at a certain height, but you can see the type of reconstruction that is going on and the quality of this wall. I have some pictures to show you the sequence of operation, the phases 1 and 2, and take a look next. This is starting from the left-hand side. How do you prepare the face of the wall? You place the FRP reinforcement, you protect it, and then how you do the casting. Again, in terms of operation, there's nothing different from what you do. Actually, let me go back here and add another item. The Ohio DOT had this request and said, okay, we understand this. You can do decks, okay, bridge decks with GFRP reinforcement. But if you want to go back and remove the existing concrete and leave the reinforcement in place, what would happen? Well, our first answer was you don't need to do it because you have no corrosion, so you don't have to replace the deck after 15, 20 years. They insisted. What happened? So we've demonstrated that you can do hydroblasting without having to damage the GFRP. So if you have the right pressure at the nozzle, you can remove the concrete without damaging an existing FRP. So I think I'm running. Oops, I'm going backwards. Sorry. I got distracted. Okay, so these are the various phases of construction. And another thing that is coming up, particularly in the area where I live, there is a requirement now to make the walls so that you can extend them in height as a result of sea level rise. So 30 years from now, you realize that you have to get another 2 foot of seawall. Can you do it? So some of these designs accommodate that. So this is kind of the completed job of phase 2, and the contractor is now working on phase 3. I probably used too much of my time, but I know that our chair does not mind. So let me get to the conclusions. And I'm not going to read them. I think you can read them for yourself. But my pitch to you is there is now no reason not to use these materials if this is what you need in your project. They are just a tool in the toolbox. They are not intended to replace steel in every application. But if you have issues of corrosion, if you have issues of savings related to transportation, if you have materials that are lower quality with respect to natural material, would they be aggregate or water, they represent an opportunity to make still good concrete. The other important statement is you have now the tools as designer or contractors to use these materials without having additional liability. Why? Because you have a code, you have material specification, and I didn't mention it, but you also have construction specs. So the 3 pillars that make projects possible are there. Obviously, the engineers will feel a little pain because they will have to learn new tricks, but this is the beauty of life, right? And we will continue doing work on this, but I think the research part, apart from the issue that I mentioned, I wouldn't say is complete, but after 30 years, we can catch our breath. And now I think is the moment of deployment, which is the most exciting one. How can we help society in making things better, last longer, and hopefully be more sustainable? Thanks for your attention.
Any questions from the audience?
Okay.
Thanks very much, Tony, for a very interesting presentation. Given the fact that the use of the GFRP, we have got the code now, and it's economically viable in comparison with our steel reinforcement, and with adequate deformability rather than ductility, why not advocate its use even in an uncorrosive environment?
Boy, you ask a difficult question. I think, to me, it's certainly a possibility. I think our industry should learn how to walk before running. So I think there is a sense of skepticism. I'll just give you an example. Miami, Florida, we build high-rise buildings, and again, Royal we. The area where the corrosion is most prominent is the balconies. You could argue, why haven't we used FRP in the balconies? Only in the last week, we are finally convinced what I would define, without mentioning names, one of the leading designers in the area to do 2 mock-up slabs so then we could load test them and convince them that everything is okay. So I think your question is a very relevant one. There is really no formal reason not to adopt it more globally, but I think to be reasonable, we still have to walk before we run. So I'm in the walking phase. I tend to be on the accelerator, but also recognize that there is the need for the brake.
Thank you.
Thank you.
How do you recycle these fibers?
Okay, wow.
At the end of the
Okay, absolutely.
life of the structure.
Okay, let me address this in 2 different ways. Very exciting topic, by the way. Today, I did not, mention it in detail. We are using vinyl ester, thermal-setting resins. So these are resins that you cannot remelt. And so there is even a let's say, some waste at the pultruder where you make these materials. But there is very intensive research now to use thermoplastic resins with the same type of performance. But if you use a thermoplastic resin, for example, there will be zero waste at the manufacturing site. The other advantage of using a thermoplastic is that you could bend the bars after they've been pultruded. That's another topic. But the question is, what if I have to demolish a structure that is made with FRP? What we believe is that the great advantage is that you can treat the FRP as if it were to be an aggregate. So you don't have to separate the reinforcement from the concrete. You basically grind everything. So I think that, unfortunately, if you were to ask me, could you prove it to me? Can you show me data? Well, we have not been in a position where we have to demolish structures made out of FRP, thanks God. Otherwise, all I'm saying would go sideways. But I think this is the intention. But let me add another item that is, in my mind, very exciting. In this country, we don't use much recycled concrete aggregate as aggregate for new construction. And the reason is because most of this aggregate is chloride contaminated. This problem, or high porosity, this problem goes away with FRP. You couldn't care less if there is chlorides or no chlorides. So I think that my answer to you, which is also a little bit of an act of faith, is on the recovery. When you get to the grave portion of the life, we are in a much better place because we can reuse this material, all of it as aggregate, without having to worry about the chloride content.
Thank you for that explanation. My question is about, again, how, from practical point of view, how to convince building officials and designers, stubborn structural engineers to use such a material. But I'm looking from the other way. We say that we could use like seawater in this design. And I didn't look at the code itself, but is there anywhere in the code that is written that you can use seawater when you are designing the structure with a FRP?
You're way ahead of me on this. No, I get it. Okay, so I think I would answer your question in different stages. Now you have the tools to say there will be no opposition from a building official. In fact, I was mentioning over lunch that we have the first project, a 3-story building, that will go for permitting on Monday. Finally, the MEP completed their design. This is a 3-story residential building with not a single pound of steel in it, from the foundation to the swimming pool. So the building official should not have an issue, but if they have an issue, we will be there to convince them. Why? Because we have a code and we have material specs. How can we convince engineers? That, to me, is the most difficult part. I think I can convince contractors because I can show the savings. You save money even in transportation. For engineers, and I apologize to all my colleague engineers today, they have to learn new tricks. So what is the incentive if you are working on a percentage, for your project? You still make 3, 4, 5%, whatever it is. So you have to learn new tricks. So the engineer is not going to be the first one to say, hey, I want to do this in FRP. So in the case of bridge structure, for example, we strongly believe that unless the DOTs mandate this, the engineers are not going to take over. Eventually, I think, as you see the first projects, and then the owners or the building official will start saying, hey, you need to do something different, it will come up. The innovation within the innovation, we're not there yet. But I think that in case of emergencies, or, for example, our colleagues in China are utilizing this without even thinking. In the China Sea, the building is being done with sea sand coming directly from the sea and seawater. They don't have any fresh water in those islands. So I think if I were to convince a code official in the city of Miami to use seawater from Biscayne Bay, I think I would have to do a little bit of homework. But eventually, I think when you think in terms of sustainability, this is where we want to be. I could go on and on. Imagine this, carbonation was our enemy, right? Because as the carbonation progresses and reaches the reinforcement, bang, all of a sudden you lost your pH and your steel goes. Now, carbonation is a blessing. Stronger concrete, less pH, I love it. So give me binders that carbonate more rapidly, like CFA, I'm ready to use them. So I think you open up a dramatic amount of opportunities. You know, some of the supplemental cementitious material or some of the new binders that have as a result a lower pH could be a blessing. So I think all this is in the making. We are on the right path, but we are a little far away from the goal line. My pleasure. Thank you.
I have a comment before you go. In my experience, I've been a structural engineer 45 years now. Every time there's new technology, new materials, really requires from the manufacturers to make the push. I'm an engineer sitting on my desk with no problems. Then there's new material. So my question, why should I get into trouble of testing? So otherwise, she's from Master Builders. Master Builder got the Riocrete to control corrosion. 30 years ago, maybe, they invited me to a seminar to see how it was used, and how to design it, and how to specify it, and how good it was. If the producer doesn't do that kind of thing, or let's say maybe 15 years ago with the carbon fibers for reinforcing structures, I'm sitting there, unless there's an ACI code, now there is now one for rebars too, and then the manufacturers go and start giving seminars how to design and specify carbon fiber. I won't use it. So it's an issue to catch up the industry. I am very proud the turn that ACI has gotten into research, investing money into research. So what maybe 40 years ago would take 20 years to get new technology to the front end, I can tell you the speed that things are moving now because of the research is outstanding, and I'm very proud of ACI for changing that direction. So this is here to stay, and I'm very proud that Tony gave us his time. He could probably keep talking until midnight about this topic. He's passionate about it, and he's really a great knowledgeable guy on this, and we thank you for your time to us today. Thank you.